Welcome to the class. Dear students, today we are going to discuss carboxylic acids, their acidity. Acidity of carboxylic acids. In this video class, we will first discuss why carboxylic acids are acidic in nature. Then we will discuss what is the strength of their acidity, what is their Ka value. Then we will compare the Ka or the pKa value of carboxylic acids with phenol and alcohol. We will find from this that carboxylic acids are much more acidic. They are much more stronger acids than phenol and alcohol. And then after finding this out, we will try to reason it out as to why carboxylic acids are stronger acids. Finally, we are going to see the effect of substituents on the acidity of carboxylic acid. So let us start. Acidity of carboxylic acids. Carboxylic acids are acidic in nature. Why am I saying that it is acidic in nature? It's because when it is dissolved in water, it dissociates to give the H plus ion. According to Arrhenius' concept of acids and bases, a substance which when dissolved in water, if it gives H plus ion, it is an acid. It is an Arrhenius acid. If you are looking so, carboxylic acid is an Arrhenius acid. Carboxylic acid dissolves in water to give H plus ion. Of course, the carboxylate ion is also formed. The carboxylate ion is nothing but the conjugate base of this acid. That means it can accept an H plus and again become RCOOH. So it's a conjugate base of this acid. Of course, carboxylate ion is formed, but the main thing is that H plus is released in the aqueous solution. So it is a Arrhenius acid. No doubt about it, right? Now the task before us is to measure its acidity. How much acidic is carboxylic acid? That we need to know so as to compare it with phenol and alcohol. So what is the acidity strength of carboxylic acid? To know the acidity strength, you have to see the extent of dissociation. From what? From the reactant. The extent of how much it dissociated from the reactant. So you have to take this in numerator and divide it by the reactant. Okay, so you will get the extent of dissociation. How much reactant was used versus how much product was formed. So you will get the extent of dissociation. Okay, so these are the reactants, RCOOH and H2O, and these are the products. So how much it is formed, you will get an idea if you divide. Am I right? Now you can remove this H2O from this equation because the amount of H2O remains constant. It is so large that only a fraction of it is converted into H3O plus. So it is negligible. Yeah, negligible amount is converted to H3O plus. So this value is always constant. So it doesn't depend upon the value of H2O because this is always the same. So it only depends upon this and how much of this is converted into RCO minus and H plus. Correct? Now this is constant for a acid. For a given acid, this is constant. Why? Because it is only depending upon the nature of that acid, which the extent of dissociation depends only on the nature of that acid. If the nature is like that, okay, it is dissociating type, then of course dissociation will be more. So it only depends upon the nature of the acid. So that is why the Ka value is constant for a given acid. Correct? The extent of dissociation depends only on the nature of the acid. So Ka value is constant. It is constant for given acid. So if we look at acetic acid, okay, the Ka value is 10 raised to the power minus 4.8. 10 raised to the power minus 4.8. Have you understood anything? Really, no. This is rather a complex way of expressing. So rather than expressing it in Ka value, we take pKa value. The pKa value is minus log 10 of Ka value. Okay. So I want to tell you here, look at this carefully. I want to tell you here that pKa value has inverse relationship with Ka value. Look at the inverse relationship, right? So pKa value has inverse relationship with Ka value. I want to tell you here at this point. and I will come back to this point later. Now pKa value, if you are putting Ka 10 raised to the power minus 4.8 for acetic acid, then pKa value for acetic acid will come 4.8. 4.8 for acetic acid. So what was the Ka value? 10 raised to the power minus 4.8. What is the pKa value? 4.8. What did I tell? This has an inverse relationship, right? The pKa value seems to be very rather small here. 4.8 is a small value. It seems to be very small. It is very small value. Smaller the value of pKa, inverse relationship, higher the value of Ka. Higher the value of Ka, greater the dissociation of the acids. Greater the dissociation of acid, greater the acidity. What did I say? Smaller the value of pKa, see 4.8 small value. Smaller the value of pKa, greater the value of Ka, greater the dissociation of the reactant and greater the acidity. So acetic acid is strong acid. Why? Because the pKa value is small. The pKa value is small. So the pKa value has to be small. If it is small, then it means that it has more acidity. Why? Because if the pKa is small, then it means that the Ka is big. Ke is a big value. Then it means that the dissociation is a big value. Then it means acidity is high. So pKa for acetic acid is 4.8, which means acetic acid is a strong acid. Now let us see the pKa value for phenol and alcohol also, then so that we are able to understand, we will able to compare it. Okay, so the pKa value for phenol is 10. How much it is? 10. I'll write it. pKa for phenol is 10. Is it a big value? No. Is it a small value? No. It's a moderate kind of value. So that means the Ka is also moderate. So that means phenol is moderate acid. Its strength is moderate. Now let us look for alcohol. The pKa value for ethanol is 60. It's very big value, 60. It means the Ka is very small. Ka is small. It means alcohol does not dissociate. It means alcohol is not at all acidic. It is kind of neutral. Okay. So the pKa value of 16 for alcohol, for ethanol, indicates that the Ka value is very small. It indicates that alcohol does not dissociate. It indicates that alcohol is not at all acidic. While phenol, it is moderately acidic. Now let us try to reason out as to why alcohol is not so acidic, why phenol is moderately acidic, and why carboxylic acid is the strongest acid among these two. Let us try to figure it out and reason it out. Why so? Dear students, I would like to remind you one thing. That thing is, carboxylic acid is strong, no doubt, but it is not as strong as mineral acid. Don't compare it with HCl and H2SO4. It is the strongest organic acid. It is stronger than phenol and alcohol, but weaker than, very much weaker than your mineral acids such as HCl and H2SO4. Don't compare it with them. Okay, let us come back to our topic, why alcohol is not acidic in nature. See this is alcohol. I am dissolving it in water. Now let us see what happens. This is the product that we get. Look at this. This is the alkoxide ion. Tell me one thing. If electrophile wants to attack it, whether it will be able to attack it with S? Yes. Very easily electrophile can come and attack. Why? Because the pair of electron is localized. It is static. It is not in motion. It is static. It is localized. So any electrophile can come and attack it. That makes the alkoxide ion very reactive. Very reactive. And very reactive means the alkoxide ion is very unstable. It is very unstable. Look at this equilibrium. The equilibrium will be shifted backwards. The formation of alkoxide ion won't be favored. An alcohol would never want to become an alkoxide ion. Why? Because the alkoxide ion is reactive. Why? Because there is localization of electron. Okay, the electrons are static, so it is very unstable. Alkoxide ion is very unstable, so the reaction is not favored in the forward direction. It is always favored in the backward direction, but never it is favored in the forward direction. Okay, so if because it is not favored in the forward direction, H plus ions won't be released as expected, and the acidity will be low for alcohol. Acidity will be low for alcohol. I hope you have understood why alcohol is not so acidic in nature. This is the reason. Alkoxide unstable, formation not favored, forward reaction not favored. Because of this, H plus won't be released as expected and acidity will be low. So that is the reason for the low acidity of alcohol. Now let us now reason out the acidity of phenol. The acidity of phenol. And why it is moderate acid, why not much stronger than carboxylic acid. We will discuss that. Let me first draw phenol. So this is the phenol. Dissolve it in water, H2O. What do you get? The conjugate base of phenol, what is it? Yes, the phenoxide ion. And what else? H plus. So phenols are acidic in nature, but whether acidity is favored, whether dissociation is favored, let us try to solve that question. So this is the phenoxide ion that is formed, correct? This comes here and this pair of electron comes here, right? Yes. Dear students, if you want to know the acidity of phenol, please refer to my earlier video where I have discussed in detail about acidity of phenol. There you will get a better idea. What we are seeing here is the resonating structure of the phenoxide ion. This same resonating structure will make it very stable. So you can see here how one complete circle, cacule form of the resonating structure you can see here, and the resonating structure of the phenoxide ion, structure 2, 3 and 4 are the resonating structure of the phenoxide ion, and structure number 1 and 5 are the cacule forms of the phenol ion. You can draw the resonance hybrid structure. It is a real structure of phenoxide ion. All other are hypothetical structures. These structures really don't exist. The real structure that exists is this. So what I want to tell you here that phenoxide ion is favored. Why? Because phenoxide ion is stable. Why is phenoxide ion stable? Because the electron is delocalized. If an electrophile, if it wants to attack the resonance hybrid structure of the phenoxide ion, whether it would be able to attack it, you tell me? No, it won't be able to attack, correct? Because the electrons are always in motion. So this motion is called as delocalization. This is called as resonance, correct? So the phenoxide ion gives rise to resonating structure. The phenoxide ion, the conjugate base of the phenol, the phenoxide ion, when it is formed, the electrons are delocalized, and this delocalization, and which is also called as resonance, brings stability, unexpected stability to phenoxide ion. And because the unexpected stability is there in phenoxide ion owing to resonance, its formation is favored. The phenoxide ion's formation is favored. Thereby dissociation is favored. Thereby phenols are acidic in nature. Because I told you the phenoxide ion is stable, Why it is stable? Because it is having delocalization of electron. It is resonance. It is in resonance. Okay, because of that, electrophile won't be able to attack the electrons in motion. Because of that, the phenoxide ion are stable. Thereby, reaction is favored in forward direction. Dissociation is favored. Correct? Thereby, your phenol is acidic in nature. I hope this is clear to you. The question before us, dear students, is why it is moderately acidic. Why it is moderately acidic? If you are seeing here, delocalization is taking place. I agree. But the delocalization is on carbon atoms. What is the nature of a carbon atom? It is electropositive. Is there any doubt? No doubt. It is electropositive. It is electron pumping in nature. Carbon atoms are electron pumping in nature. Now, will it be able to absorb electron pair within its orbital? Will the carbon atom be able to absorb electron pair within its orbital? Never. Why? Because electron pair, it is pumping in nature. It tries to pump electron. Carbon tries to pump electron. It is electropositive. So it is pumping in nature. So it would never absorb the pair of electron. Okay. It would never absorb it. Correct. So there is delocalization. I agree. But that delocalization is not effective. Okay. There is no absorption or there is no retention of the negative charge anywhere. Okay. It is always outside. Okay. So delocalization is there, no doubt. I agree. But that delocalization is not so effective. Why? Because the delocalization always occurs on electropositive carbon atom, which itself is electron pumping in nature. Thereby they cannot absorb the electron pair within their orbital. Okay, so the delocalization is not so effective in case of phenoxide ion, and thereby it is acidic on account of resonance, but moderately acidic because there is no effective resonance. The resonance is there, but it is not 100% effective. So that is why it is moderately acidic. I hope you have understood the concept. Now let us see the acidity of carboxylic acid. Why carboxylic acid are highly acidic, more acidic than phenol. Let us see that. When we see the carboxylic acid, then we will better understand phenol also. Look at carboxylic acid now. So this is our carboxylic acid. I am going to dissolve it in water, and we are going to get the conjugate base of carboxylic acid, which is the carboxylate ion. So there you go. This is double bond O, H3O plus minus. Another case can occur when this can go here and this can go here, and what you get here is this. Correct? So this is resonating structure 1, this is resonating structure 2. Let me put it in bracket. Can we draw the resonance hybrid structure for these? This looks like this. Sometimes bond is formed here, sometimes bond is formed here, and negative charge is here. Or you can put like this also. Half of the time, half of the negative charge here and half of the negative charge here. Okay, I would prefer to put like this. Okay, negative charge. Now look at the carboxylic acid. Carboxylic acid is also acidic. It dissolves in water to release H plus ion. But is it very highly acidic? Yes, it is very high acidity. It has got good acidity, high acidity. Why? Because the carboxylate ion formed, the conjugate base of carboxylic acid, the carboxylate ion that is formed, they exhibit resonance. They show resonance. They show delocalization of electron. There are two resonating structures, and we have shown the resonance hybrid structure. The real structure is the resonance hybrid structure. These are imaginary structures. So the negative charge is between the two oxygen atoms. It is consumed by the two oxygen atoms. Oxygen atom, what is the nature of oxygen atom? What is the nature of oxygen atom? it is electronegative. It is electron withdrawing. It takes electron. It sucks electron. Okay. So this electron pair is effectively taken into the orbitals of oxygen, which are electronegative in nature, which are electron withdrawing in nature. So the electron pair is effectively taken into the orbitals of the two electronegative oxygen atom. Therefore, there is delocalization. I agree, but the delocalization is specifically made very effective because of the presence of two electron withdrawing groups, or because of the presence of two electronegative oxygen atoms. Okay, so they can absorb the electron pair very well into their orbital, and that would decrease the negative charge outside, and thereby the delocalization is very effective. The stability of the carboxylate ion is very high. So that is why the formation of carboxylate ion is favored, and the reaction will always proceed towards the forward direction, releasing more H plus into the system. Thereby the acidity of carboxylic acid is very high. That's the reason why the acidity of carboxylic acid is very high. I hope you have understood the reasons behind this. There is resonance in carboxylic acid. It is a proven fact. Okay. How it is proven fact? X-ray diffraction measurements show that there is resonance in carboxylic acid. Okay, if you are seeing the X-ray diffraction method measurement, the carbon oxygen bond in carboxylic acid COOH group, okay, and if you compare the CO in your alcohol or in your ether, right? So this is much shorter, this is shorter, okay, and this is longer. Okay, this is 1.43 Armstrong. Okay, and this is 1.30 Armstrong. Why this is shorter? Because this is 1.5 bond. Okay, here, correct? The resonance hybrid structure, it's a 1.5 bond. So that's why this bond is intermediate. There is no single bond. Carbon oxygen single bond in COH doesn't exist. It is always between sigma and pi. It's an intermediate character. Okay, so it's 1.5 bond. That is shorter in carboxylic acid. How much short? 1.30 Armstrong. And it is longer in alcohol and ether. How much? See, 1.43 Armstrong in alcohol and ether. Okay, another proof, X-ray diffraction method also show that carbon oxygen double bond in COH is no doubt it is longer. Okay, because it is not carbon double bond, it's not a double bond, it's always intermediate between double and single bond. It is always longer, and carbon double bond in aldehyde and ketone, it is shorter because it is pakka double bond, no doubt. But this is not a pakka double bond, this is intermediate. Okay, this is about 1.23 Armstrong and this is 1.20 Armstrong. So X-ray diffraction method is proving that there is resonance in carboxylic acid, and because of this resonance only carboxylic acids are acidic in nature. Okay. Now molecular orbital, this thing is there, molecular orbital picture of carboxylic acid and the effect of substituents of carboxylic acid. There are two more topics left. One is the molecular orbital picture of carboxylic acid. The other topic is effect of substituents on the acidity of carboxylic acid. These two topics we will cover in the next video class. Dear students, I hope you have liked the video. If you have done so, if it has been useful to you, please do not forget to subscribe the channel. Do share and do like it. Thank you very much.